Professor, today we have Professor Hui of Nanjing University, I think the School of Earth Science, Nanjing University, telling us the finding, the discovery of I would say relative significant amount of water in some of the lunar rock coming from the interior or the mantle of the moon, which has changed our idea that the moon should be extremely dry. So it has an important implication on the formation process of the Earth-Moon system. Professor Hui, can you start now?
Okay. Yeah.
Thank you.
Good afternoon, everyone. Thanks very much, Professor Ip, for the invitation. I will talk about water in the lunar interior, distribution and evolution. My talk will first talk about models about the formation and the evolution of the moon, and then I will give a brief history of the debate of lunar water, and then what evolution in the moon, and I will briefly talk about what distribution in the moon. Finally, and about the origin of lunar water, and then I will give a short summary, brief summary. All right, and I think likely all of us know about the moon formation based on the giant impact theory. Theia, a Mars-sized planetesimal impact with the proto-Earth about 4.6 billion years ago. This is the ejected material coalesced to form the moon near the Earth. This basically is a violent energetic formation of the moon. Following this impact, material coalesced. Just a second. Somehow. Material coalesced through gravitation attraction impacts, inducing large-scale melting to form the lunar magma ocean. Actually, this lunar magma ocean model was proposed just after the return of Apollo 11 samples to Earth. So based on this this model, the young moon basically was covered by a global magma ocean. When the temperature decreases, olivine and pyroxene began to crystallize and sank to form the primitive mantle. Around at 75 or 80% of the lunar magma ocean solidified, plagioclase started to crystallize, which the density is lower than the residual magma, and floated to form the primitive crust. As the magma ocean continued to crystallize, eventually at around after crystallization of 95 or 98% of the magma ocean, there's a magma layer left. This is basically called air creep, which is enriched in potassium, rare earth elements, phosphorus, and other incompatible trace elements. So in our lunar sample collections, we often see the creep materials like creep basalts, some impact mills, which also contain creep signals. Basically, these materials were contaminated by air creep. So that's why they are enriched in these incompatible trace elements. So there are several evidences to support this lunar magma ocean model. Here I will introduce only two evidences. One is basically is a ferroanthracite. As I just said, the plagioclase crystallized in the magma ocean because of its lower density. It floated to form the lunar crust. So this ferroandesite actually is the relic of this primary crust. And also, it is the only sampled lithology from the lunar magma ocean in our lunar sample collection. And the other evidence I show here is actually European anomaly in mire basalts. As we know, the mire basalts actually is the solidified melt, which originated from the lunar mantle. As we can see from all the mire basalts, no matter whether it contains high potassium or low potassium, or high titanium or low titanium, and also from different missions, all these mire basalts shows a universal European negative anomaly, which indicates that the lunar mantle is depleted in European relative to other rare earth elements. So this means the lunar mantle basically formed through a global lunar magma reservoir, i.e. here is the lunar magma ocean. So basically both the European anomalies in mire basalts and the widespread occurrence of ferroandesite supports the existence of the lunar magma ocean in the Yang. So as we know, both the moon's impact origin, its energetic formation, and also this lunar magma ocean, both these processes are actually has a very high the temperature was very high. That means most volatiles would be lost actually based on these models. As we know, the like silver, bromium, indium, zinc, these moderately volatiles will be partially lost. For the hydrogen, noble gas, these very volatile elements would be completely lost during these processes. In our based on for the early observation, actually we did observe that volatiles in lunar materials are depleted relative to the earth materials. Furthermore, for these lunar materials, that we do see there's heavy zinc isotope such as zinc 66 enrichment in lunar materials. So this leaves the question is hydrogen. How about water? Whether water is depleted or it's completely lost in the lunar samples. For the during the Apollo missions, as we can see, is first of all there was no liquid water on the moon, and also from analysis of the lunar materials, we can I will show you the early results about the hydrogen contents or water contents in the returned lunar samples. Before I step to the hydrogen or water contents in the lunar samples, I will first introduce a few terms. So first one is about water in lunar materials. So water here means in geochemists or cosmochemists, we call those molecular hydrogen hydroxyl and molecular water, all call them just water. So basically it's a collection of hydrogen species in lunar glasses and minerals. For the minerals, typically includes nominally anhydrous minerals, such as like olivine, pyroxene, and plagioclase. And also for the lunar materials, we also have nominally hydrous mineral. There's actually only one nominal hydrous mineral, which is apatite. In the lunar materials, we also, there's another material which we will introduce, which contain the hydrogen species, which is melt inclusions in minerals, such as shown here. This is like melt inclusions in olivine grains. Of course, here's the picture I show here. This is actually is not lunar mineral. Actually, this is terrestrial olivine. But I will show you that actually we did detect hydrogen in olivine melting inclusions from the Apollo 17 samples. One more thing is what I'm going for the H2O here. I said for water, is H2O equivalent in parts per million by weight. So then I will start to give a brief history about the debate of water. I will separate into two parts. One is before 2008, after Apollo missions. So actually, just after the Apollo missions, or even during Apollo missions, lots of lunar materials were analyzed for hydrogen isotopes, especially those the analysis. Those some samples analyzed at Caltech, and we see is the hydrogen isotopes in these lunar materials actually are a mixture of terrestrial water vapor and the solar wind. So basically is one for the terrestrial water vapor, that means it's terrestrial contamination. As we can understand this because these samples actually were shipped to Houston and stored at JSC, and during this transition, actually these some of the samples actually we exposed some sort in air. So it's since Houston is humid, so it could contain contaminated by terrestrial water. And another thing is the solar wind. Basically, is these materials were impacted by the solar wind particles on the lunar surface for billions of years. So this is why the signal is from solar wind. So basically, this mixture is we can understand the mixture of these two sources to explain the hydrogen isotopes in lunar samples. The other one is a very famous rock. It's from Apollo 16. It's 66095. It's called a rusty rock because this rock was discovered that it contained rust. So if as we know, if the material contains rust, that means it must have some sort of when it's the rust formation of the rust must contain some kind of water. However, this the isotope analysis shows that actually this hydrogen or this water actually also is a contamination of terrestrial water vapor. This rust, the formation of this rust can be explained by the reaction between water vapor and the lawrencite, which the lawrencite actually is a native mineral in this rock 66095. And it reacted with water and hydrogen, oxygen on Earth, and formed this hydrous iron material, and so that's why it became rust. Of course, so this is not from the moon. Actually, it's a contamination of terrestrial water vapor. One thing I should note here, this sample has been reanalyzed in the last several years. Of course, it's not about mainly it's not about hydrogen, but about the other volatile elements, such as sulfur in this material, this rock. So it do contain some indigenous volatiles from the moon, but for the hydrogen in this rust, actually it's not. It's from terrestrial contamination. And furthermore, actually some materials, some lunar materials, like clinopyroxene, glass beads, were also analyzed by infrared method. However, in 1990s, the detection limits for the infrared instrument is higher than 50 ppm. As I will show later, the hydrogen, the water concentration actually is very low in the lunar materials. That's why in the early time, the infrared cannot detect water in these lunar materials. There are also some other observations were carried out in 1990s, like for the whole rock measurement for hydrogen. Basically the measurement shows that the water concentration in the whole rock is less than 50 ppm. Another thing is no hydrous minerals except apatite have ever been discovered in the lunar materials. So that's why all the early analysis suggests that the moon is bone dry. As we know, in 2019, a paper published in Nature and challenged this bone dry view of the moon. It's a group of scientists from Brown University and some other institutions. They detect water and fluorine, chlorine, sulfur in these lunar glass beads. Here is a figure from their paper, which shows that in one glass bead, the core of this glass bead contain high water content and also volatile elements, other volatile elements than the rim. This suggests that the water or fluorine, chlorine, and sulfur must not the contamination from the laboratory during analysis, because if it is the contamination, then it would mean the rim contain more water than the core. And of course, for the fluorine, chlorine, and sulfur, these are not typically cannot be contaminated in the laboratory. So based on these evidences, they basically they showed that these lunar glass beads contain water, and they further calculate water content in the glass parent magmas. That showed that these basaltic magma could contain up to 750 ppm water. So this is a completely different view from the bone dry moon. They showed that it's a wet moon, and analysis continue to carry out not just the glass beads. They also, and scientists, actually several groups analyzed the apatite, and they showed these apatites are actually also contain water, and also the Harry and Albert Saul, they analyzed the olivine melt inclusions in the Apollo 17 soils. They showed that all these studies show that this is a wet moon, and some parts may be very wet, especially those olivine melt inclusions. They contain up to 1400 ppm water. As I should mention here is most of our analysis of water actually were carried out on apatite. As I showed earlier, is that apatite actually is normally hydrous mineral. As we show here, that the apatite in its formula, it contains hydrogen hydroxyl. So this for this hydrous mineral, in 2014, Boyce and his colleagues show that the water content measured in lunar apatites actually cannot be directly used to infer the water content in the parent magma. They showed that actually in here is that apatite in marble salt 12039, as we can see, all these elements profile. They did carried out profile analysis along this apatite grain. They show that these major elements are correlated with each other. Actually, we can understand it that because of the fractional crystallization. So that's why that's why these elements were correlated with each other. But for the fluorine and the water, and we can see they are opposite. They show in the opposite behavior, and the water content in the apatite can be explained by also the fractional crystallization. Basically, is the apatite first incorporates fluorine, and as the crystallization proceeds, the water fluorine ratio increased. That's why at the apatite rim we can see is the high water content. So basically, this figure shows that the water content in the apatite cannot be used to interpret water content in the parent magma, which means that hydrogen-rich apatite is not necessary to mean that the magma is water-rich. So this is this shows that actually the water content measured in apatites, probably we shouldn't say it's useless, but it's not very useful to infer water content in the lunar interior. However, the hydrogen isotope in the lunar apatite is very useful. In 2011, Greenwood and his colleagues analyzed a lot of apatite grains from different lunar samples. They showed that these lunar apatites, the hydrogen isotope of these lunar apatites show that there are several sources for the water content in the lunar interior. Basically, one is from the solar wind. The other one is indigenous water that in the lunar interior, and also it's from the comets. So based on these hydrogen isotope compositions, they show there's multiple sources for the water content in the lunar interior. On the other hand, two different groups use the hydrogen isotopes in different materials to infer the source of the lunar water based on the glass and the melting inclusion. Albert Saul and his colleagues, they showed in their science paper that the delta D in the lunar magma is about 187 per mil, and for the on the other hand, the Barnes and his and her colleagues showed that in the highland apatites, the delta D is about minus 200 per mil. So basically the difference is very large. It's about 400 per mil difference. However, both groups, they said it's the hydrogen isotope, based on the hydrogen isotope in the lunar materials, indicates that water in the lunar interior shares a common origin of water in Earth. So this is like caused there's a big difference, but they get to the same conclusion. But based on the previous studies, we have a new moon, which is the lunar interior contains water. But on the other hand, we still not sure where the source of the water or the origin of the water. So this water may have been added by impacts. On the other hand, the primary lunar water is possible. So now I will introduce my contribution on the lunar water study. So based on this question is what is the source of the lunar water? We tried to understand one question is was the early moon wet or dry? So as I mentioned earlier, there was a lunar magma ocean in a young moon. So during the magma ocean crystallization, the primary crust actually formed from the lunar magma ocean, and ferroanosite actually is a relic of this ferroanositic crust. So if we want to know whether the young moon or early moon contain water, so one sample we could analyze is this ferroanosite. So we carried out this analysis. We analyzed the platyclase grains from ferroanosite 15415 and 6015. I should say these plagioclase are actually not very ideal. They're full of fractures and also melting inclusions. As we can see, this is a mineral grain from plagioclase grain from 15415. As we can see, there are fractures, and also these dark spots actually are the mineral inclusions. For the FTI analysis, we made 1 millimeter mineral sections for water analysis, and we also use the SIMS, secondary ion mass spectrometer, to analyze the water content in these mineral grains. So for the SIMS analysis, small polished pieces were embedded in the disk for analysis. Actually, what I want to mention here is both grains in our studies actually were analyzed by both FTI and SIMS. As well, I will show in the next a few slides. So I first show you the FTI results. Here is the FTI spectra of plagioclase grain. This plagioclase grain from sample 60015. As we know, for the plagioclase, actually it's an anisotropic mineral. So if we want to do a quantitative analysis, means we want to get the water content from this mineral grain, we have to obtain the. Ideally, we have to we need to obtain the infrared spectra from 3 crystal axes, but for these lunar samples, it is extremely difficult to obtain to polish the grains along these 3 directions. So we simplified this method. We analyzed we obtained the FTI spectra along 3 perpendicular directions. So here is shown as EXT1, EXT2, and EXT3. They are perpendicular with each other. And based on the spectra, the absorbance here, I show here above this dashed line, we calculated water content. It's about 6 ppm water in this grain. We also analyzed the plagioclase grain from 15415. Unfortunately, these grains are smaller, and we can obtain 2 polished surfaces from these grains. And that's why we can only obtain 2 spectra from 2 perpendicular directions. So we can only get a minimum water content, minimum water contents in these grains. We also demonstrate whether since this water content is really low, we also carry out dehydration experiment to demonstrate the water content in these grains are not from laboratory contamination. So we did a dehydration experiment. We also prepared this grain in the same way as those grains analyzed previously. we show that the grain after the dehydration experiment, it does show this absorbance peak actually is smaller than original one. That means the hydrogen we measured are actually is in the pelagic crystal lattice defects. That means it's from the moon. And we also did seams measurements on these grains, and I will skip these the details about this method. I direct show you the results. So basically, is we obtained the hydrogen water contents in these pelagic grains and show that these grains from 63535, 15415, and 60015. The pelagic grains from these three samples contain the water content from about 3 to 6 ppm. These results are consistent with our FTI analysis. For the seams measurements, actually, we can obtain not only the water content, we can also obtain the hydrogen isotope compositions. So we analyzed the hydrogen isotope compositions in the plagioclase grains. As we showed in the early slides, that the water content in these grains are very low. So for these samples, which were on the moon surface for millions of years, we had have to correct the irradiation effect from the cosmic rays. So after the cosmic ray corrections, only the hydrogen isotopes in 6015 is meaningful. For the other two, because of the corrections, the error bar are too large. But we still can use the hydrogen isotopes in 6015. As we can see, the hydrogen isotope in this plagioclase grain is about 300 per mil. So if we plot all the hydrogen isotopes in the lunar materials against their sample ages, we can see is in this figure is these orange circle, they show is actually these are the data from the degassed basalt. As we can see is that because of degassing, the hydrogen isotope ratios can increase in these these basalts. So that means the hydrogen isotope data in these degassed basalt do not represent their parent magma isotope compositions or their source, the isotope compositions of their source regions. On the other hand, as we can see from these old samples, for the fine manganese sweet or alkali sweet, these are plutonic rocks. That means the degassing effect is minimal. So the hydrogen isotope compositions in these samples can be used to represent those of their sources. And also for the melting inclusions, because these inclusions are protected by their host crystals. That means their hydrogen isotope composition can be used to represent their parent magma i.e. their source region. Then means we can use all these old samples to understand the hydrogen isotope compositions of their source regions. Here, I want to discuss about 6015 and 14305, which is an alkali suite. So it's protonic, and 74220 actually is melt the hydrogen isotope data from the olivine melting inclusions. As we can see, these three samples, the hydrogen isotopes in these three samples are actually are very similar. For 74220 actually is orange glass beads. That means it contains very high titanium contents. So that mean this also means their source regions actually inherited from the later crystallized lunar magma ocean products, the ilmenite. And for the 60015, as we know, this is ferroandesite. So it's also late crystallized. We can see that their source regions basically have very similar isotope compositions. So we can interpret this as probably it represents the hydrogen isotope compositions after the formation of the crust, the lunar crust. So the degas of the lunar magma ocean became minimal. That means these source regions have similar isotope compositions. For 78235 and 77215 actually are the manganese suite. From the igneous, the petrogenesis of the manganese suite, we know that actually the manganese suite represents the material, basically the material which is the mixture of the lunar crust and lunar primary crust and the early formed lunar mantle. So this we know is the accumulated mantle formed earlier than the lunar crust. So that means these manganese suite may contain a source region which crystallized in the early lunar magma ocean. In this case, we can look at these three samples, 6015, 78235, and 77215. And we can see if we plot the Radiance junction isotope data and also as a trace element data, we can see is that these three samples are actually a mixture, show a mixing trend between these three samples. So if this is the case, that means for the hydrogen isotope, we can also explain. We can also explain the hydrogen isotope relationship between these three samples. So basically, is that we could explain the hydrogen isotope composition is of these three samples are correlated with each other, and then therefore we can calculate the hydrogen isotope compositions in the early melt accumulates crystallized from the lunar magma ocean, means much earlier than the crystallization of the primary crust. So based on this this interpretation, we can say for the hydrogen isotope compositions in the early lunar magma ocean is about minus 270. So based on the degassing of the lunar magma ocean, and then we can calculate the water content in the initial water content in the lunar magma ocean using the water content in the the ferroanocytic plagioclase, and also the water partition coefficient between plagioclase and the melt. So we, based on these data, we inferred that the initial water content in the lunar magma ocean likely was higher than 1,000 ppm. For a reference is in our primary mantle of Earth is about 1,100 ppm. So based on all the early sample analysis, we show that the lunar interior contains water. However, as we could see from this this map, most of water data of the lunar samples actually based on 6 Apollo missions. So as we often think that these sample sites likely do not represent a global distribution of the cannot represent the a global moon. So this the water concentration in our lunar samples can support that whether water is distributed locally or is like in these 6 landing sites or globally. To answer this question, one thing is we could do a remote analysis of water. Actually, this is carried out by Millikan and Lee from Brown University. They used near-infrared reflectance spectra from M-Cube. And based on these infrared data, they showed that there is a widespread occurrence of water in pyroclastic materials. As we can see from this figure, these red areas indicate these are actually also the pyroclastic materials. They showed that they contain high water content higher than the rest area actually is background. So they show that these pyroclastic can contain up to 150 ppm water. And some areas, like potential vent areas, contain as high as 400 ppm water. And this observation is not related to the material, the chemical compositions of these pyroclastic materials, the latitude and longitude, I mean the locations. So that means this is likely a globally observation. So that means there's widespread indigenous water in lunar pyroclastic deposits. This supports that the lunar interior contains water, not just locally, but rather a global observation. So now we can see that the lunar interior does contain water, and also in the history of the evolution of the moon, it also contained water. One question is, what is the origin of lunar water? Based on our hydrogen isotope data, we showed that even the initial lunar magma ocean also contained water. So one spontaneous answer probably is like the water is inherited from the formation material of the moon, which then means the giant impact actually did not devolatilize all the water in these materials. That means it's kind of contradict to the giant impact theory of the moon. On the other hand, Barnes and his colleagues used the hydrogen isotope data and mass constraint. They calculate that the majority of the water actually was from the water-rich chondrite, and minor contribution also from the deuterium-rich comets, but less than 20%. However, this water has to be delivered in a very short window in the moon formation. That means the moon received the delivery of these volatile the water by asteroids and comets during the initial stages of the planetary differentiation. That means for the initial lunar magma ocean stage. However, this is excuse me. The origin of the lunar water actually is still debating. Okay, finally, I come to this short summary. So the moon contained water at the time of the lunar magma ocean crystallization. Hydrogen isotope fractionated due to the degassing in the lunar magma ocean until the formation of the primary lunar crust. And also the remote sensing data shows that widespread indigenous water in lunar pyroclastic deposits. However, it is still not known whether water could have survived during the formation of the moon or added by asteroid impacts during the lunar magma ocean crystallization. Okay, I think that's the end, and thank you very much for your time.
Yeah, thank you so much, Professor Hui, for your talk on the study of the water inside the moon. Now, I have a question. There is where did you get the lunar material for your analysis? I mean, I mean, you must have this in the lab. You must have some lunar rock or lunar grass, right, to do this analysis.
I analyzed lunar plagioclase when I was in the United States.
Okay, you will how's it, piggyback, right? Now, are you planning to do the same thing with this lunar sample collected by Chang'e 5?
Yeah, I think we will try to do that. And actually, the CNSA just announced the call for the application of the lunar samples. Yes, yeah, we will apply for the samples to do this kind of analysis.
I'm
Yes.
sure you will. And do you think that it will help you to solve the problem? You know, I mean, the origin of this kind of water, would that help you to solve the problem using this new lunar samples?
I think the thing is, well, based on some, some initial results I heard from in person, not official one, official date, official yet. These samples are younger, so it cannot result. I think these samples are likely the ideal ones to understand to know the early water or hydrogen concentrate, hydrogen isotopes in the old samples. But these samples are young samples, probably around around 2 billion years old. So it's much younger. So likely they can explain other things like the evolution of water content in the lunar interior, in the lunar mantle. Yeah.
So this is a channel 5. You know where the channel 6 is going to go? I mean, they also doing a lunar sample correction, and where would you recommend them to go?
I would suggest go to the South Pole. It has old samples and also the materials from deep interior. Likely, well, not sure, but likely from the deep crust, or even probably some in the shallow mantle.
Okay, I think that I hope that your wish will be fulfilled by your agency. Yeah. And thank you so much, Professor Hui, because the time is up, and the Dr. Lebrun, Francois Lebrun is waiting. And then you are welcome to listen to him. You know, he's going to talk about the exosphere of the moon.
Okay. Right.